And we should be live. My microphone is going. Okay, so welcome to another live on our research project on the assumptions of physics. And what we plan to do today is to go back to the topic that I already discussed in a video a while back on essentially the need for a more suitable formulation, interpretation, whatever you want to call it, of differential geometry for physics so that we can have a sense of what the elements mean and how units are handled and have a notation that becomes a little bit more intuitive for the things that we need to do. So what I'm going to do right now is set up my tablet so that I'm gonna write as if we had a whiteboard. Though we don't have a whiteboard, I have a tablet on which I'm going to scribble on. So let's see if this works. Start because it's this share screen, this and then this. Okay, so hopefully everybody should see my tablet.
Yes, I can see it.
Very good. And I should turn up the volume so that I can hear you a little bit better. Okay. So the main problem is that one does so the real purpose of differential topology is to generalize a series of notions that we have in vector calculus such that we can work in essentially any dimension. So the problem with vector calculus is that it works great for 3 dimensions, but it doesn't work outside of 3 dimensions, mainly because it assumes that there is only one perpendicular to each surface, to each plane. And so you identify planes by looking at the perpendiculars, and this only works if you are in 3 dimensions. If you are in 4 dimensions, there are infinitely many perpendicular to a plane, and therefore it doesn't work anymore. So the idea is that you need to track planes by tracking pairs of vectors, essentially, and volumes by triples of vectors and so on. And so this is essentially what differential topology allows you to do, and then these tools are then inherited by differential geometry and so on. The issue is that in order to make some constructions nice and things to prove nice and so on, the space of vector is defined as the space of derivation. So in differential topology and differential geometry, typically your vectors are given by the partial derivatives of, for example, the coordinates. So this would be your vector basis. And so a vector v would be something that takes a function, so a continuous functions on our space X, and returns another continuous functions on our space X. Right, so this thing, for example, would get the f in a particular direction. So this would be a vector, and the vector would be basically a derivation in a particular direction, and this is just another function. Right, so the vector v is essentially vi partial derivative with respect to xi, right? And this is a map, right? It's a map that takes us a continuous function and gives us back another continuous function.
Well, the
Okay.
function should be at least differentiable, right? Obviously.
Yeah, yeah, differentiable. I mean, smooth function, I meant to say. So, there
Uh,
should be an infinity here.
can you maybe turn down the thickness of the lines? I think that might make
Yeah,
it more readable.
we are very fat. Let's see. How do I do this? Is this better? Yeah. So this would be like V. Yeah, this works, right? Okay.
Yeah, much better.
Okay, so This is how you essentially define vectors, and then there is the notion that these are tangent vectors because they're defined locally. But for now, that's not really the problem. That's going to be work out. That has to work. And then differentials are defined as maps that take a vector and give you back a number. So, and again, you would have a basis of the differentials, which be your dxi's, and each df is something that takes a vector. Let's call the space of vectors v at a point. So, well, space would be a vector field anyway, and then returns, well, in this case, would return a continuous function as well, right? No, returns a number. There you go. And so, for example, you would apply dxi to the vector, let's say, let's pick up a particular one. Let's pick dx1, and we apply to this vector, and this would give us a 1. And if we add instead the dx1 applied to partial in dx2 in another direction, this would be 0. So we would have the general form that this is the Kronecker delta. It's 1 if the two indices are the same, and it's 0 if the indices are different. Okay, so you have this thing. The issue is that these are not the objects that we want to describe in physics when we are talking about vectors and differentials and so on, right? So one of the things that the differentials are useful for is then to be able to integrate. So you would want to write something that there is an integration over a differential, let's say df. And the way that this is supposed to work is that there is an implicit parenthesis here where you're giving essentially the vector that corresponds, so a vector v that corresponds to the shape that you are integrating of, right? Like that. That's basically what is assumed. And this is a little bit backward for what we want to do in physics, because the way that we think integral, for example, would be something like this. We are going to say that work is the integral of a force over an infinitesimal displacement. So the infinitesimal displacement in it has to be our differential, and the force is going to be our covector. So the force is the thing that takes the infinitesimal displacement and gives us an infinitesimal amount of work, right? So we would like to say essentially that f I is the infinitesimal work over the infinitesimal displacement, where we would like to ideally make sense of something like this. Of course, this is a problem that this is in principle not a number. We can't divide it by that, right? So those are the things that we want to kind of make sense. The other thing that and so basically what we have in physics, the way that we typically think about vectors and functions of vector, is that in this case the vectors is this guy, right? So we would like to work with something that looks like this, and now we want to say that this is our infinitesimal displacement dp, and the force, well, the force. And we can write it like this. The force is the function of the displacement. So the force is the thing that gets the displacement and gives us back a number, which is going to be dw. Right, so there is some kind of inversion that happens when you are, writing things like that. The other problem that this hides, that this approach hides, is that it doesn't work with units. So if I say that these are my base vectors, dx and dy, right? Of course, like if you imagine, right, I can sum these two things if and only if the units of x and y are the same. And if I am in something like polar coordinates, I would have something like this. This is an r. And I would have a theta on the other side. And I can't sum these things. And you can say, well, whatever, we can fix the unit by putting here a coefficient that fixes the unit. But if you're assuming that, you are already assuming that you have a geometry on the space that allows you to do that. That allows you to say that a specific length in this variable is equal to a specific length on this variable. So you're basically saying, okay, I have a geometry. But the whole point of doing differential topology is that all these ideas of vector tangent spaces and exterior derivative and so on are available to you even if you don't have a geometry. Or even if you have totally different geometry, like you have Riemannian geometry for space and you have symplectic geometry for a phase space. So the idea that, oh, we can just fix the units later, it already like breaks the fundamental assumption while you're trying to build these tools. So that doesn't quite work. And then, of course, there is the problem that if I'm thinking of velocity, if I'm thinking of displacement, those are not derivations, so that they are starting different. And so this is the problem that I want to fix because I want a real one-to-one correspondence between the mathematical objects and the physics that it's describing, so that when we draw a picture, right, when we draw a picture of an area, a region, and we have vectors that come out, right? That's the actual thing that the math is representing, right? And now these vectors that come out would be derivations over some, there's some going vi over dxi, so some derivation. This is what these vectors are, and so it becomes a little bit more like the math is not really what you're describing, and then it becomes very difficult to interpret what are the things that you're interpreting. Does that make sense?
Oh, I'm already unmuted. Yes, that makes sense to me.
Okay. So that's basically it. And then the question is, can we do it? And yes, of course, we can do it. So the way that the thing is supposed to work, and let's just make a simple example. Let's say that we have a space like physical space X, right? That you can imagine as a standard three-dimensional space. And then we have a trajectory over the space. So let's say that it's a time evolution, just to make it a little bit more concrete, right? So we have, this is X, the space of our three-dimensional space, and then I have small t that represents time. And I have a function, gamma, right? That goes from time to space, right? That's what I have. Now, what we want to do, right? Typically, when we think about integration, derivation, and so on, we want to be able to break this trajectory and in little pieces and see what's happening in each neighborhood. So ideally, we would like to have for X a parallel space, which we call, let's say, dx, which is the space of all the infinitesimal displacement in X. And we want to have a space of infinitesimal displacement in T. We call it dt. And at that point, since we have a gamma here, we are going, if gamma is differentiable, right? Then what's going to happen is that every infinitesimal, then we can make a map at each point t. We can make a map knowing if we had this displacement in time, how much displacement we would have in space. And this would be a map between displacement, and this is going to be our d gamma over dt. This is going to be our velocity. So we can understand the velocity as the map that takes a dt and gives us a dx. And at that point, we can write it as dx over dt, because what's going to happen is that this map is linear, and since it's linear, we can think it as simply, when we have our dx, we can just think of the dx as being the velocity times dt. Right? So the fact that we're writing the velocity as a dx over dt, in this case, is just a notation convenient. It's not that we are really taking the dividing by dt, it's just that we are going to have a map between differential and differential. Now, if we think of derivation like that, then we can do it essentially the same procedure between any generic space. So, for example, let's suppose now that we have the space of possible temperature, and then we're going to have a temperature map that tells us at each point x what is going to be the temperature. So again, I will imagine that there are going to be infinitesimal displacement in temperature, and now I'm going to have a map that tells me for each infinitesimal displacement in space, what is going to be the infinitesimal displacement in temperature, right? And this map is going to be our df over dx, right? Because it's going to take a small dx and give us a small dt. And what's going to happen that this, if we write it in components, this is just going to be the gradient of the temperature, right? The gradient of f. And again, because if we give this a displacement, right, then we get our displacement in t. And with the same idea, we could have a map that goes from an Rn to an Rm space, right? So if we have a map like this, then we can imagine the space of differential on one, the space of differential on the other, and then we would basically be able to write, let's call this x and let's call this y, then we would be able to write dy over dx. And again, the fact that we have the d's even on objects that are not numbers anymore is just a convenience for us in notation, so that when we write the chain rule, we can just put the d's on top on the bottom and everything works, and then there's nothing else. So this sort of grounds a little bit these ideas. And of course, ideally, I'd like to have this done well in a mathematical language. The space of differentials should basically be the set of sequences that converges with some kind of nice property, and then you make an equivalence class of these things, and then you can define that space, show that it's a vector space, and then show that there are maps and so on. And so I have some building blocks for that that needs to be sort of how can I say, formalized nicely. We need to understand whether, because in principle they could be generalized in some interesting ways, but maybe for the physics we're not going to be interested in doing that anyway, so maybe we just leave it as they are. So this is basically the general idea. And once we have these types of objects and this definition of derivative, one of the things that should come as a bonus is that the only requirement that I need on these spaces here is to be at least locally a vector space, so that I can define derivatives in a way that already looks like variational derivatives, which is what we use in function spaces. So when you are when doing classical field theories, you typically write the variation of your field or your variation of the Lagrange and so on. Those are basically differential type thing in the sense that we're written, like infinitesimal displacement, instead of being in a finite dimensional space like you would be in Rn. They're in an infinite dimensional space because functions are infinite dimensional. So another thing that I'd like to have is essentially a notion of derivative, a notion of a tangent space in quote, which is the space of differential, done in a way that we literally use the same definition both for the finite dimensional case, the infinite dimensional case, and we have objects that sort of maps well to the physics and so on.
So you would even want the same definition for like distributions, like the Radon-Nikodym derivative? Would it
Okay,
be
so
same?
the link to measure theory, that's another thing. Yes, in principle, I'd like that there is some kind of tight connection between the derivative that you use in measure theory and this type of derivatives. Also because the forms are in a way something that I want that I think generalize the type of derivatives that you have in measure theory. The way that one may do that is that if you think of a manifold, and if you think of well, let's say a vector space. Let's assume that we have a vector space. Easier for now. And you imagine the space of volumes, right? Since these volumes can be divided and so on. So if you imagine a space of variations for volumes, right? So I have a volume, now I stick in little volumes around. That also should, I think, form a vector space in a way that I think there should be standard construction for this. I'm just not fully aware of them and how they would work. Now, in that case, then you would be able to sort of redo the same ideas, you reapply the same ideas, not to vector spaces of, let's say, made of points, where the vector represents a point, but where the vectors represents volumes, right? So the displacement is a displacement of volume, like it's a change, a variation of volume. And the Radon-Nikodym derivative is essentially a ratio of values that are assigned to a volume. So if I have, let's say, a measure of probability, right? A measure of probability takes some type of volume. Let's say, let's call it, let's takes a region, right? It takes a region U, and it gives me a real number from 0 to 1. And then let's say that I really have a volume measure, like the Liouville measure in phase space, something that really tells me what a volume is, or the volume in physical space. And again, I will be able to give it a U and look at the positive real number that volume is. When you're doing a Radon-Nikodym derivative, in a sense, you're kind of doing this. You're taking the probability of U divided the volume of U, and you make it where the U essentially goes to a point, right? You make the volume smaller and smaller and smaller. In the limit, you make it a point. So it is again a function that goes from function spaces to function spaces, except that you're doing like something different. And so again, you could think this as, let's say, they call it d rho d mu. The way that we should again think it in terms of what we said before, let's say that we make a variation on the volume, right? We make the volume a little bit bigger, a little bit smaller, then we're going to get a variation in the probability. So this essentially, in terms of differential geometry or in differential topology, should become a volume form, right? So the way that you would write these type of things in differential geometry is would you say, okay, I have a volume V, and this is the integral of some volume form, let's call it rho, and it's integrated over let's say, well, let's not call it V. Let's call this M. Let's say that this is a mass. This is a mass density, and my dV is going to be my infinitesimal volume, right? And now this becomes a form because the way that you think about this volume as really being given by a 3 infinitesimal displacement. But these 3 infinitesimal displacement, right, it's together they form a vector space as well, right? It's because it's just the product of the vector spaces. And so ideally, I'd like to have a something that tells me in a way that it's a little bit more tight, the relationship between this type of limit here and this type of limit here, or this type of derivative, and show that they're the same thing. And what I'd like to have then is to be able to do this type of relation regardless of the dimensionality of these things. So the typical way that I think about this, we said before, I have a work, and work is a force times a displacement dp, right? This is typically what we write. And then I have a magnetic flux, and a magnetic flux is a phi, which is a magnetic field cross product with some infinitesimal area. Let's call it d sigma. And then I have my mass, and my mass is the integral of the mass density times my infinitesimal volume, right? This is how we do things in vector calculus in 3 dimensions. But again, the way that we can rethink about all these is that this is an integral of f that takes a single infinitesimal displacement. This is an integral on a magnetic field that takes two infinitesimal displacement, dp1 and dp2, and the two infinitesimal displacement make the area. And this is my density, and my density is a function that takes three infinitesimal displacements. And since these are things that act on volumes and areas, if you switch the order, right, these are going to be signed elements, and you get a minus sign, right? And that's basically in differential geometry, that's what a form is. A form omega is something that takes n vectors, right? So it's a function, a linear function of n vectors, and it gives you a real number. And it's fully antisymmetric, meaning that if you switch two elements, you get a minus sign, right? And again, to me, now this beta, I can sort of think it as, sorry, this B, the magnetic field, I can think it in some kind of infinitesimal contribution to the flux over the infinitesimal areas in which I'm doing the flux. My work was my, well, dB, no, B. My force, I can think it as the infinitesimal contribution to the work over the infinitesimal displacement, and my mass density is going to be my infinitesimal contribution to the mass under my infinitesimal contribution, my infinitesimal volume, right? And now that you have this pattern, the idea is that this now works in any dimension. And if you have a phase space that it's 10 billion particles, you have the 6 billion dimension, but you can still talk about these things in a sort of meaningful way. So does that answer the question?
Yeah. So for measures, the space would be like some sigma algebra, and then we will need to define what like a d volume is, like a somewhat of a difference between two volumes, and if they are small enough, we somehow can define a vector space or something.
Right. There should be some construction that should allow you to do something like that. Because we can go from one way of looking at things to the other. So there has to be a nice way to do it. And the interesting part is going to be when you do things like these, right? There has to be a nice, like when volumes are nice because there is only sort of one way to shrink like the volume, because it's you take the three coordinates, you shrink it down. It's with surfaces you have at a point you have very many like you can be on, even if you just look at the planes, right? You have many planes, so many different way of doing the variation. So there has to be a way that this function, because at this point this is going to be a function of the surfaces, this is going to be a function on lines, and this is going to be a function of volumes. But it has to be in some sense, a differentiable function of the surfaces and lines and volumes. And the lines and the surfaces themselves have to be differentiables in some sense, because otherwise you wouldn't be able to define all these things on top. And teasing out all these assumptions would allow us to understand what are the physical requirements that you are implicitly putting in when you're saying, oh, I have smooth functions, I have smooth functions of smooth surfaces, and so on.
And if that these assumptions would be broken, we would say the full, like the W is defined, and I cannot find an F, right?
Right.
Okay,
Yeah.
and the other way around.
Right. So that's exactly what I would expect, because these are the things that are connected to measurement. So we measure the work, we measure the flux, we measure the mass on finite surfaces. The infinitesimal is the limit. And so you're assuming that you can make that limit, and for example, that the limit is independent by how you're taking the limit.
Yeah, that makes sense to me.
And so the goal would be to then reinterpret. So the first step would be just to reinterpret all the things that one already has in differential geometry and differential topology with this approach. And it's partly what I did to be able to find a physical and geometrical interpretation for the action principle. And once I did all that deconstruction, like it's much easier to see the physics, because you know what all the little symbols mean, and so you can start drawing pictures, step by step, and have a better understanding of what's going on. I always find so, as I said before, the problem of units gets completely thrown out, but actually keeping the units there and understanding whether, what are the units of these things helps you a lot in keeping track of the physics. And again, there are still some things that I don't quite understand. For example, when we write a Poisson bracket, right? We write F and G, right? Like this. What are the units of this thing? Well, they're units of F and G, but hidden inside here, there is essentially a division for the units of the symplectic form. Right? So there is implicit a units of area that you are defining, because if you write this fully, you have something like this. G partial P minus partial G partial Q partial F partial P, right? So on top, you have the products of the units of F and G, clearly. And on the bottom, you have the product of Q and P, right? And you see already this notation hides that. You wouldn't be able to see that if you weren't doing. So this is kind of a density of units of F and G over units, areas of phase space, right? And so that ties in. Like if you don't realize that the units downstairs is, there is a division of units of space, you don't understand that those things are density, then it's more difficult to understand what is it that these things both geometrically and physically represent. If you keep the units and you do the dimensional checking, then you get a little bit more of a sense of what's going on. So for example, when you write the F over dt is equal the Poisson bracket between F and the Hamiltonian, right? This is a unit of F over time. Okay, this is a unit of F times Hamiltonian, right? But then you're dividing over units of phase space, which is equal of Hamiltonian over time. And then you see, okay, now these two cancel out. That's why this makes sense. all of these things are completely hidden by the math. You don't see them. And if you write things in coordinates instead of this notation, you do see it better, because the Poisson bracket in the coordinates would be something like this. Partial A f, actually there is a minus, partial A f, then omega. Symplectic form, I do lowercase omega, yes. And then AB, partial BH, right? And now this is going to be df over dt. Right? And now you can see here explicit that this is the inverse of the symplectic form. So this has units of inverse omega, right? When you're taking your derivatives here, and so you recover. You can see better that there is something going on in terms of units. And this is again why another thing that I want to do is to re-express as much as we can the notation that you have in differential geometry in terms of components, because now when you have components, you can understand better what's going on. There are some expression that you're doing in the differential geometry that are just that if you write them in component, like you might have expression A, expression B, but when you write them in component, they are the same thing. You're just breaking the expression in two different ways. So for example, you might have VI partial F partial XI, right? Now you can imagine to break this in this way, and now you have a vector applied to F. Or now you can also imagine to break it this way, and you had some other expression in terms of the coordinate-free notation. And so it's kind of, to me, that the coordinate-free notation sometimes makes it harder to follow the proofs, because yeah, you're hiding all these issues, and I don't know. I just find it a lot more convenient.
By the way, I'm not sure if I know what vectors are in differential topology. I guess I only learned like differential geometry, where I always have a manifold. I guess in differential topology, I don't have a manifold.
No,
Can I
you have
still-
manifold. Differential topology is essentially everything that you have in differential geometry without the metric tensor is differential
okay.
topology.
Okay, yeah, then of course that exists. Okay, fine.
Yeah. So the differential topology is basically the manifold plus the differentiable structure, so that you can talk about the tangent space, you can talk about differentiability, and you can talk about you can define the sort of the Lie derivative of vector fields. You can define the exterior derivative and stuff like that.
Okay.
Yeah, so the exterior derivative is another thing that it's, and the Stokes theorem, that it's a lot simpler understood in integral form than in differential form. So once you realize that these things, right, all these functions are basically just functions of shapes, right? So you can say basically, I have a function, let's call it t, that it's a function that takes a point and gives me a number. Right? And then I can imagine a function w that takes a line and gives me a number, right? Now, given this, I can always create another one of these, because suppose that I have, my space, I get a line, right? And I have my line gamma, and I have a function t of the point. I can always decide to, let's say, call this A and this call it B, right? I can always define W of gamma as the difference between the value at point B minus the value at point A. Now, I can always imagine that I also have my function of my sigma, of my surface. Well, now what happens is that if I'm given a function on a line and I have a surface, right? Now the contour of the surface is a line. So given a function on a surface, I can always define the function by giving the boundary of the surface. And again, you can say, oh, now I have a function of a volume, and this gives me a number. And again, you can define the function of the volume by taking the function and apply it on the surface. Okay? And there's like, of course, you can always do that. Now, what's interesting, of course, is that if you make the boundary of the boundary, I think I have the something wrong here. This is could be the boundary of the volume, right? What's interesting is that if you make this thing twice, right? And I started with a W, right? So now I have a W of a boundary of the boundary of the volume. Well, the boundary of the boundary is always zero. It's the empty set. And if these things are linear, the function applied to the empty set it has to be zero. And so what happens is that you can always do this, this definition only one step up. If you do it twice, then it's sort of you're gonna get a functional that is always gonna be zero. And this is exactly the integral thing, the integral expression of taking the exterior derivative. So when you have a form omega, you can take an exterior derivative, and this gives you a form of, if this is an n form, this is going to be an n plus 1 form, right? And we saw before, the form is something that you give it an infinitesimal parallelepiped, and it gives you back a number. So it's the forms are the infinitesimal version of these things. And of course, it is a result in differential topology that if you take the exterior derivative twice, you get the zero form. And this is why. Because if I start with a surface and take the boundary of the line, and now I want to take the boundary of the boundary, so the boundary of this line, well, the initial point is the same as the final point. There is no boundary. And so now when I apply the function on the point, I'm going to apply it to nothing, and I get nothing. And so this works at any dimensionality, right? And it's something that you can draw a picture. It's very simple to understand in the integral form. And in the differential form, instead, you have this definition of the exterior derivative with wedge products and blah, 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 and so on. And then you have to prove that this thing, if you do it twice, you get something that is always zero. While, again, if you draw the picture, it's like completely obvious.
Okay, actually, the exterior derivative always confused me. I only know this formal thing, and then you have a wedge product, and then you do it twice, and it's antisymmetric, and it cancels, and like, why am I not allowed to take more than one derivative? That's kind of weird.
Yeah. So the way that I write the derivative, so we have a wedge product. So the wedge product is something that if you imagine that I give you two forms, right? So I have a form and another form, and I do a wedge product. What you're basically doing is making the product on the volume. Like you're giving me a function on the volume where you're using one form on one side and the other form on the other side. Right?
Yeah.
That's what the project, the wedge product is doing. Right? It's taking parallelepipeds and forming forming functions on the parallelepipeds made. So I guess I should write it like this. So let's say that we have an omega on V1 and V2, right? And then I have a wedge, let's call it, I don't know, what is another letter for forms? I don't even know. Let's call it mu, whatever. And then this is on another vector, right? This now is going to be another form lambda of V1, V2, V3, right? So this was taking an infinitesimal surface, right? This was taking an infinitesimal surface. This is taking an infinitesimal distance. Now this is taking an infinitesimal volume, right? And the way that you're calculating the sort of the volume of this volume, right? The volume of the parallel pipette is just calculating the volume on the two different things and calculating, right? And so if we have a form and if we write it in component, the components are down. So this would be an ij, and this would be a mu k, right? Because this is going to accept vectors, and vectors are up, right? V, W, and U. There you go. Right? And so this now gives you an invariant because you are contracting. And by the way, the fact is these indexes are up and these indexes are down. These are exactly units, right? These are units of the vector, and these are inverse units on the vector. And so that's why they cancel out, because now you're making, it's like you have a meter and a function of meter that gives you an invariant. Well, then that function has to be an inverse meter because it has to take the meter, cancel it out, and give you something else, right? So if I have work, right, and I have a force here, right, and I have a distance, right, clearly the force has to be of units work over distance, right? And so this index down really means this is an inverse of the units of distance. And this is, again, something that gets completely lost when you're doing differential geometry because, you're doing math, everything is numbers, and then, but, if you think it like this, it's just like that. So now when you're making an exterior derivative, the way that you should think about it is that these are the components. I have a derivative in I, and wedge the derivatives in the form applied in all the other directions, j, k, right? And so now this gamma is going to be a form of I, j, k. Okay. Now, if you imagine what's
Wait, say
going
again,
on,
what is that? That is the exterior derivative?
yeah,
Okay.
you're making the wedge product with the partials. That's it. That's the notation that I
Okay, yeah.
use, and again, it makes evident what's going on. And geometrically, the way that you should think about it, you have your j and your k, right? And so this is your j, your k. But now you have an I, right? You have it twice. So this is the j, this is the k, and this is the I, where you're taking again the j and the k. And the derivative means that you're making this minus this, right? It's, let's say, let's call this, A, your A, let's call it this B, and this is A. So the form applied on B minus the form applied on A. You're making a difference. And this is exactly, if I had everything worked out nicely in my head, I could show you that this is exactly what's happening when you are doing this business here in the infinitesimal. That's essentially what you're doing. And so there is a more geometrical way to understand this that links to that. Right now, I don't have it yet. Right now, I have at least the math that shows you at least what's going on. You're taking the form in each side and making the derivative on each form. You're taking one minus the other. But yeah, that's basically going to give you something that when you sum it all up, then it's gonna give you the contribution only on the boundaries. I don't know if this helps in any way, but these are the intuitions that I think if one sits down and does all the work, then you are going to end up with a nice set of pictures, a nice set of equation that sort of tells you exactly what these things are.
Okay, so if I if I would have a top form as a volume form, I don't even I can only choose an eye that is already like in the plane. Like it would be like in the plane of K and J, right?
Yeah,
So since it's a linear function, nothing will happen, right? So that's why it would be automatically zero if I have
it
a
would
top
be
form.
automatically zero because of the wedge product.
Yeah.
Because the wedge product is antisymmetric.
And even geometrically, if I just
Yeah,
shift in the plane,
yeah,
obviously since it's linear, nothing changes. Okay.
yeah, yeah. Yeah, yeah. So yeah, geometrically, it's that, and then mathematically, you see because there is the antisymmetry there, because you're essentially doing the vectors applied first in the direction of their variation, and then on the other time in actually where you are calculating the form itself, and so the two things are going to cancel out. And again, I can guarantee that if you sit down, you're gonna be able to find a nice, clear examples for all these things that, of course, it has to be like that because otherwise it doesn't work, right?
Okay, for what you had up there was two derivatives, right? So I would need to do this twice and then say see that it's always zero,
Oh, for
independent of
that,
dimension.
again, it's even easier, right? KL. It's antisymmetric.
Yeah, I mean algebraically, yes.
Yeah.
I mean geometrically.
Geometrically, you just reason like we were reasoning before. I think it's just so much easier to think it in the integral form. But
Of course, yeah.
in principle, you should be able to do it with parallelopipeds, right? Because let's say we just you start with points, right? You have 2 points, and then you are gonna have no, you have to. You see, I have two. Yeah, okay. I don't have it right off the top of my head, but you should be able to like the volumes and all those stuff becomes parallelopipeds, right? And so you have one direction for this. We have like one direction in which you're taking the form, and the other direction that you're taking the derivatives. Right. And so you should be able to construct, again, you know what these, how this maps to this, right? So you should be able to make the construction step by step and see that you just get a zero.
Yeah. I'm afraid we might need 4 dimensions because we take two derivatives, but it should work.
Well, you make this a form of just one thing.
Yeah, maybe that works. Yeah.
Yeah. Yeah.
Just
And
for
then
intuition, if M would be a form, like, and it's defined on a vector space and it's linear, like the mass of a little volume.
yeah, the density is the form.
Okay, just
Okay.
if it would be already, so if I had a constant density, I guess,
Mhm.
then M would be linear if it's defined on a vector space, not on a manifold. If I then take dm, would I get rho?
So rho is dm over dv.
It's not immediately that. It's like the comparison between the two forms, somewhat. Like
Well,
the normal volume form and the
it's the function of the infinitesimal parallelepiped. So dv is the infinitesimal parallelepiped. You give infinitesimal parallelepiped to the mass density, and then you gives you an infinitesimal change in the mass.
Okay, so dm takes little parallelepipeds.
The rho takes infinitesimal
Rho
parallelepiped.
does that.
So the rho, like you have to think it as a function of the infinitesimal parallelepiped, right? So rho takes three vectors, and three vectors gives identify an infinitesimal parallelepiped, and then it gives you a dm.
So dm itself is what kind of function?
It's a real number. It's a well, it's a variation of the mass. So you can think it
Okay.
as you know a limit of a change for the change becoming smaller and smaller.
Okay, yeah. For a given variation in V, it's the variation in M.
Right. So you can imagine again what we'd like to have like formally, like conceptually, you have the space V of volumes, right? All the possible volumes. And then you have a space of dVs that are infinitesimal variations of those volumes around a point, right? So you have a
Yeah,
point, and at that point you make a change in the volume. You add a little bit of volume, or you remove a little bit of volume, right? And then you have the mass, which is a real number, and then you have a mass function that takes a volume and gives you a real number.
yeah.
And then even here, there's going to be a space of infinitesimal changes of the mass, right? And then you want to say that the density is something that, given an infinitesimal volume, gives you the infinitesimal mass. So given an infinitesimal variation on a volume gives you the infinitesimal variation of the mass.
Okay, that makes sense. But just like you can confuse the function M with M, I think I confused the function rho with dm.
Yeah.
Okay, yeah, but then my intuition is good
Okay,
at.
good. Yeah, so this is where mathematician would be a lot more well, unconfused. You said that m was the function, and now you're saying that the m is the space. And this is where exactly physicists said, oh yeah, there is a mass, there is a function from one to the other. I call the target or the function in the same way. That's how I think it anyway.
Sure. This is even like when they Fourier transform, they just change the argument from x to k, and then it's obvious that this is the Fourier transform of the
Yeah.
function.
So it's actually a very convenient thing because once you have like, I don't know, three different or four different spaces that are all linked to each other, right, in this way, right? You can express this one in terms of this in terms of this, or this in terms of, so you have all these permutations. And if you were to write the name of all the possible maps, right, you start having a combinatorial effect. While if you only write the starting space and the ending space, right, it scales better, right, because you don't go combinatorially, right? And so there is actually an actual advantage of using that notation, and the important thing that it's clear what the map should be, and oftentimes in physics it's clear what the map is. So that's why you do it. Yeah, and the other thing that I kind of had in my head, but I never really written down, is that this way of looking at things gives you even a geometric proof for um, I don't remember the name of the theorem, but the fact that if you have let's see, a closed form, you can write in a neighborhood an exact a form that it's whose exterior derivative is the target form. So you can basically make potentials and vector potentials. So if you have a form omega such that the omega is equal to 0, then in a neighborhood you can write that omega is the exterior derivative of a theta. And I don't have it read here, so I don't think I would be able to just write it down. But it's all a matter of when you have lines, it's easy, right? If you have lines, well, you can basically say if my form on lines is closed, then if I have my, if you imagine to having your W of gamma such that this is 0 for any closed curve, right? Then you can basically say, okay, if I have 2 points, this part is equal to this part, and then I call this 0, and now I can call this as essentially the W applied to one of the paths. Like what happens is that you can do the same thing with surfaces. Like if you have something that is a function of surfaces, you can do the same trick. I can take the thing and cut it, and then it does not depend on which way. Like it only depends on the boundary. It doesn't depend on the surface across the boundary. So now you can give the number to the boundary. What happens is that you have to do a little bit of a step further, and you need to be able to essentially take the boundaries and cut them again and give an arbitrary number to half of the boundary. And now this is going to tell you what numbers you have to apply to the other half of the boundary, which is exactly what happens here, is that the boundary of a line is made of 2 points. And so you give an arbitrary value to 1 point, and then you have the value of the other point all determined by the function of the line. And so when you generalize this, you have to do the same thing. Now, every closed curve, I can see it as essentially one side plus the other side. And as long as you give essentially an arbitrary value to all the possible lines from 2 points, then that's you know how to close the curves. And what it turns out is that this arbitrary value that you're giving is exactly the choice of gauge. In the same way that the choice of gauge here is just a constant function over the full space. Now here the choice of gauge is a function over lines. And it's actually going to be the gradient of a function, because the closed loop always has to give you 0, otherwise the thing doesn't work. So again, there is this is something that I never written down. It's half baked in my head. There is a way to understand all of vector potentials and so on, and gauge choices as these choices on half boundaries, essentially.
Okay, by the way, I think you use some kind of functions like the work depending on a curve. That is on a manifold, right? And then you get a df that is just a form on a tangent space.
You get an yes. So you have your W is going to be the integral of some form f, right, over all over the path.
Yes. So, but the big W is not a form yet. So that's a bit different from just taking exterior derivatives of forms, because then everything is a form. But here we start initially with something that is on the whole manifold. And then once we take one derivative, we get forms, and then does it make sense?
The form is just the integral version of the function on the submanifold, essentially on the curve.
Yeah, okay. But for example, in the omega equals d theta. Omega is a form and not like a function on a manifold or like
Right.
on of curves on a manifold and stuff like this.
So what happens here is that we are going to be able to write F, right? Let's see. As so this, right? If we say that this work is path independent, then we're saying that df is equal to 0,
Yeah.
right? And now we are going to be able to say that f is the exterior derivative of some scalar function v.
Okay, yeah.
Right? Which basically, if you write it in component, this is this. And since there is nothing to antisymmetrize, this is just the gradient of v. Does that make sense?
Yeah. So this is it comes from a potential. It's a potential force.
Right. It's a
force.
potential. And the way that
Yeah.
you see geometrically, you say, okay, if I have 2 points, any line that connects them, right? This value is going to be the same. So the integral of the form along the path is going to be the same, right? So this value here only depends on the point. It does not depend on the path which you arrive to the point. And then you say, okay, I will give to this point, I will give the value v, right? V is equal that.
Yeah. Yeah.
And what I'm saying is that the same reasoning works for this phi, which of course now it's a phi of sigma, and it's going to be an integral over sigma or of my b, right? And my b now is my 2 form. And I know that this is closed because the flux of a magnetic field over a closed surface is 0. So dB is equal 0. Right? Now, what's going to happen is that since the flux is on a closed surface in 0, if I have a closed path, the flux through the closed path is the same regardless of which surface I get within the closed path. Then I can, if I imagine cutting the closed path in 2 parts, that's exactly like separating the boundary of the line into 2 parts, the beginning point and the end point, right? So this side here, this is your beginning point, and the other side is your end point. And then you can assign a 0, an arbitrary value on this curve, and then the other side of the curve is going to be determined by the flux. Right? So we want to be able to say that that B equals DA, right? And now with an A, we can imagine that we have, let's call it, what can I call it? A good letter. Well, let's call it a C, right? I could imagine that I have a C that given a gamma, I just have the integral over gamma of A, right? So on this one form, I have a corresponding function of lines. And so I say now that this C of this particular gamma is going to be 0, and now the C on that other gamma is going to be phi of the flux in between. Right? In analogy of what I did here. Like this I called V equals 0, and this I called V equals the work applied to that gamma. Is it understandable?
Yeah, that makes sense. Still, I feel like what you wrote up there, like omega equal d theta. The theta is a form, and now, for example, down there you have a di like dv. F is dv, a potential. The potential is a function of the whole manifold. It's not a form. So I think there is like
No, the potential is a form.
the potential is a form, but I mean
It's a zero form. It only takes a point. It does not take a vector.
at each point.
Hmm?
So
At each point, it takes no vector.
You still,
Right?
so you just need to integrate all of this stuff somewhat.
So
Not integrate, but it's like you have to extend it to the whole manifold in some. It's not just on a tangent space.
the forms are defined at every point, at every tangent space at every point.
Yes, okay.
Yeah.
Yeah. Okay, I was just so you cannot just think of like one vector space. You really need to think about like all the tangent spaces and the whole manifold.
Yeah.
It just confused me, yeah. But otherwise it's clear.
Yeah. When you're taking the exterior derivative, you're doing something that is linking together the vector spaces at points that are infinitesimally close to each other.
Yeah.
So you wouldn't be able to define derivative over the space if you just had the vector space at one point.
Yeah, I know that makes no sense.
Yeah. So yeah, these are the things that so sometimes I think, oh, I should just stop working on the ensemble space and just take this and write it down now or nicely, or I never know what I should be working on. I'm always confused. But yeah, these are basically pieces that I feel that anybody could, with some guidance, uh, take them and sort of shape them into something more final, and then we would publish a paper, do videos or whatever. So if there is anybody watching this video that wants to help me write or do those nice because they want to understand it for themselves, and then writing it down for other people forces you to understand things a lot better for yourself as well. So that would be a task that I'd be happy to take people to work on. Yeah, that's basically the brain dump. Then there is some of the mathematical detail, but I think the mathematical detail is just it is just that you do it if you really want to go and get into the nitty-gritty detail. Like I thought we just do an overview for today. I don't know if you have any questions, if there is any question in the chat. Otherwise, we can just drop for today.
So you had an approach, right? Of defining a derivative on a topological vector space,
Yeah,
like these sequences.
yeah.
Is that the approach we want to find out how far it goes?
Is what?
Do we want, this is the approach we want to take, so I should check how far it goes.
Yeah, so there are basically two ways, right?
Yeah.
It's again reverse physics versus physical mathematics. You can basically say, look, let's start with sort of the higher level structure and trying to re-understand those better, and just even give like nice re-notations or re-understanding of those without worrying about too much in with the mathematical detail. Or you can say, okay, let's start from scratch, get a definition of derivative, make sure that it works in the general case, and then make sure that all the cases that we want to cover are going to be covered by that general definition. Right? And so it depends which way you want to go.
Okay, so what you've done so far looks more like the reverse physics style.
Today, we basically did that. Yeah.
Okay.
Because we said, okay, we have this bunch of math, is not quite what we want, but it's not really formulated in a way that we want, but we want to be able to do those operations. It's just that we have a misidentification of the mathematical objects with the physical objects. And so we want to be able to fix that such that we can reason about these things better, right? That's what we did today. Then the other thing would be, okay, let's start from scratch and really make the mathematical definition match exactly what we want them to say, right?
Okay. I think I first need to do a bit of reverse physics as well, just
Yeah,
for my intuition, because
exactly.
yeah.
That's how I operate too. Like if I don't have, I think, and this is like I think the problem also that a lot of sort of like more mathematical approaches on the foundation of physics at the end of the day run out of things. That if you don't have the right intuition to start, you don't even know how to guide the formal definition.
Yeah, I agree.
Yeah. So the bits, some of these bits are already there in the book for the um, when I have sort of the differential topology discussion in the book, it sort of goes and says some of these things. I don't know. I don't remember what level of details they go through. And so one other thing that would be possible again, and again, I tried having somebody write a thesis on this, so that it didn't quite work out. But the idea would really be to make this dictionary, right? So when we talk about an exterior derivative, what is it that we're talking about? We're talking about this, and then have all the description in terms of functionals of surfaces, such that you get because again the intuition you're gonna get the intuition a lot better if you think about this side the function of lines, points, and surfaces than on the form. The form are just you take those things and you shrink them in the neighborhood at the infinitesimal, right? But the real intuition you get by thinking about lines and surfaces and volumes and stuff like that.
Okay, I don't want to stretch it, but I had like one random idea recently, and maybe it's related.
Go
Uh,
ahead.
I was thinking again about going from Hamiltonian mechanics to Lagrangian mechanics, which is
Hmm.
not always possible. You need to somehow identify momenta and velocities, right? You need
Yeah.
kinematic equivalence. That is somehow going from cotangent bundle to tangent bundle.
Hmm.
And usually, I'm not sure if it's the physically correct identification, but you have like an isomorphism between a tangent, a cotangent, covector space and the vector space given by the metric.
But the metric already assumes that you have a kinematic equivalent.
Okay. So um then I remembered, okay, this is how we incorporate this. Okay.
Yeah.
Then we had like, or at least I had one counterexample, which is somewhat exotic, but kind of works, which is if you have photons, you don't know what the momentum is if you only know the velocity.
All right.
Velocity is always just c.
Mhm.
Um, in that case, if you had photons, I guess you should look at like proper space-time, and you don't have a metric, you have a pseudometric. Is that maybe why you cannot identify anymore, like along the uh light cones, like tangent to the light cones, you don't have this identification anymore between the two vector spaces. I was just wondering if this breaks for this reason.
No, so for the photons, you really need the field. Because what's going to happen is that when you're going to have the field, the velocities become the change of the field instead of like the speed of the field, right? The change of the field at the point. And that's when you're going to be able to make conjugates, and then that's where
Of course.
where you can get a sort of Hamiltonian treatments and like full treatment of the photons. Otherwise,
Sure, that's why it's slightly exotic. Like we wouldn't think of photons as like point particles. But
right.
the point particle, like the point photon, is the counterexample where you cannot use wait, you cannot use Lagrangian
Yes, yeah,
because yeah, you don't know the momentum.
yeah. But in that case, if you just limit like that, you basically so the metric tensor is the map that allows you to go from the momentum to the velocities. So if
Yeah.
you're just looking at the phase space, it's not really a phase space, at the state space of photons, right? In that sense, you do not have a metric tensor because you can't go back and forth.
Okay.
Even though there is a metric tensor in space-time, that structure does not allow you to, like, you need something else to tell you.
Would I even have, could I define like a symplectic structure on like a pseudo-Riemannian manifold? Is that a thing?
No, so all the Riemannian geometry, right, does not even have um, I can say, a constraint on the dimensionality, right? So you could have, in fact, physical space, it's three-dimensional, and so you already know that it can't be symplectic, right?
Okay, but I mean, you can start with a Riemannian manifold,
Yep.
then just define there's a canonical symplectic form on the cotangent bundle. Is that
Yes.
correct?
Yeah. Sure.
If I start off with a pseudo-Riemannian
Yeah.
manifold,
You're gonna have the same thing. Yeah.
okay, you're gonna have the same thing.
Yeah. Yeah. Yeah.
Okay.
You always have the cotangent bundles. You can always define your what's it called? Uh, there's a canonical one form, I think it's called. And then the exterior derivative of that, it's gonna be closed and
Okay, by the way, this always confuses me. Why is the canonical symplectic form? Is it also the physical one, or could they be different? And when are they the same?
well, that's kind of the issue, right? So, mathematically, you can always do whatever you want, and whether those things are useful or not, it's a completely different.
Yeah, I was just hoping if they can do it. Like either it's not possible to do it canonically, but apparently they just can. And then I'm like, why is this even possible? Like if it has physical meaning, I don't know. If I need like some physical input to decide which symplectic form is the correct one, I don't understand why you can define one without this physical input. Just, or maybe it's just like, I don't know.
Because you're working on different sets of objects. So the way that, again, you can think about this construction is that, okay, you have a point in Riemannian space, okay? And in fact, I don't even think you need Riemannian geometry at that point. You just have a differentiable manifold, right? I have a point, and at every point, I have the space of all the tangent vectors, which are, in this case, the derivations, right? So of course, I can always define the derivations at points, and I can always do that. Okay. Now, remember, the form in their context is a map from a vector to a number. And of course, I'm always going to have a vector space that takes those vectors, sorry, a vector space made of the functions of basically the dual of the vectors, right? Of course, that always exists, right? And that's the cotangent bundle. It's the set of those functions which always exist. The issue is, again, that we are not looking at those things. We're looking at velocities and we're looking at momentum. And momentum is not a one form. Momentum is another state variable. It's something else. When we talk phase space, I think it's completely improper to say that that thing is a cotangent bundle, because position and momentum are just two state variables. And so if you think about the way that you think the state space, what is the state space? It's a set of points that determine the full state of the system, and the state variables are those numbers that allow you to identify what is a specific state of the system, right? So
Yeah.
conjugate momentum is just another state variable. It's the same as a position, right? In that term, it's a number that you need to identify the space. So it's not a function of anything. Momentum is not a function of anything. It's a number that you go and provided that you fixed some definition, you can go and measure, right? And the fact that there is this cotangent bundle structure is the fact that the momentum, conjugate momentum, has to have units that are inverse of the units of position. That's the physics that really is there. Is that there is a special set of coordinates that are the conjugate momentum that have this nice property, which you need because the way that you count state has to be coordinated invariant. Now, the fact that these momenta have this physical property of being inverse units means that now you can identify a map between position and momentum and an element of the cotangent bundle. Because the cotangent bundle has these similar properties of variation under coordinate transformation. But it's an accident that the two things have the same mathematical properties. There is nothing physical about the fact that momentum is a map.
Also, if I only need like any, no, I don't need any kind of second or variable or even more variables in principle to define the state. Like if that's my only requirement, there is like that's very limited constraint on what the variable is, right? Any kind of bijective function of that would still define the state. But then I guess you want to use another coordinate that lets you count states properly, right? That gives you the unit constraint.
Sorry, I didn't.
So if you just say I have a state space,
Yep.
that means I need enough variables to fully determine what the state of my system is.
Yes.
Then part of that is position. That kind of makes sense. And then we just need more variables. Like turns out we need more to fully determine the state. There's almost no constraint on what that variable is, right? If I have like just a bijective function and I just relabel my states,
Yeah.
it still uniquely determines whatever happens.
Yeah, exactly. So when
but
we
then you want to use the second variable. It turns out we need two. Actually, it turns out we need two because of units as well, right?
Yeah.
So you want to measure like the count of states using that second variable together with position.
Yeah.
So actually any kind of coordinate on your configuration space, I guess.
Yeah.
Okay,
In fact,
and then we get this kind of, then it becomes more structured, and then we see it looks like a cotangent bundle.
right.
Okay.
But again, the fact, so when we change state variables and we say position momentum instead of position velocity, right? We haven't changed the space. We have only chosen a different set of coordinates for the manifolds and need different set of variables. So the idea that when we go from momentum to velocity, we go from a cotangent bundle to a tangent bundle. It's a little bit of a nonsense because we are still in the same manifolds. We're still describing states. We're still describing the same things. We just chosen a different representation. Now, the representation might be isomorphic to a cotangent bundle or a tangent bundle, whatever. If we're doing math, we can. But again, it's all accidental. We could use completely different variables that are neither position, and sorry, neither momentum and neither velocity, and we don't have a structure either of a tangent bundle or a tangent bundle. We just have the states. And it might be that for some physics problem, that might be more convenient, right? When you use action angle variable, for example, right? In Hamiltonian mechanics, you separate things and you use action angle variables, right? Those variables now, there's not going to be a position in the same sense that there is a position in in physical space, right? The constant could be an arbitrary function of position and momentum, and the action angle variable would circle around in some trajectory that it's a mixture of position and momentum. So there are a lot of these things where people are trying to mathematize these things, but again, they do it because the mathematical structure are nice, but the physics is not being given its right place.
Okay.
Yeah, so I'm happy, to keep talking about cotangent bundles and tangent bundles in my head, because in my head I have the map and I know that that's sort of, so when I talk to mathematicians, yeah, okay, fine, that's the language that they are used to. I'm perfectly fine to adapt. But I think talking, if you're making a physics class, right, and you're teaching these things and you're talking about these things as if they matter, I don't think you're teaching physics at that point. You're just confusing things.
Okay.
Okay, so let me unshare here. Here. And stop share. There we go. Any other questions or objections? Yeah. So I don't have ideas for next time, by the way. So I was trying to invite somebody else, but I had no luck. So we'll discuss on Discord. Okay, so we'll end it here. And if people have a suggestion for the one they want to see discussed in these lives, that's also okay. Please leave a comment. Otherwise, see you next time.
Okay. See you. Thanks.
See you. There we go.